Swayam Prabha. Digital India. Educated India.
Hello, good afternoon. Welcome to the course on comprehensive view of speech processing. So today is the fourth lecture. So far we discussed about the introductory part of speech processing. Today we'll discuss more about speech production perception from a human perspective. So this is the block diagram for speech production perception from a human perspective. So the top one is the from a production perspective. As a talker as a person, when he want to convey the message, then the human counterpart will be a talker, and he from the message he pick up a language based on the target listener, and then the message as per the target as per the message is nothing but as per the sequence of words. The corresponding neuromuscular commands will be issued to the vocal tract system or speech production system. Then articulators will be moved accordingly. Then the corresponding speech will be generated. So from the listener perspective, it's just the reverse phenomena. Like the speech will be captured by our hearing mechanism, and that hearing mechanism will convert the speech to the nerve impulses, and these nerve impulses will reach to the brain, higher centers of a brain, and where the message interpretation will take place. So these things we discussed in the last class, and in the last class we also briefly discussed about speech production system with the help of this figure, and this is the cross sectional view of our speech production system. And speech production system involves the lungs assembly and the connected windpipe, and then here this is known to be the laryngeal cavity where the vocal folds will be there, and then beyond the vocal folds is known to be pharyngeal cavity. This cavity is in between the space that is between vocal folds and the velum, that is the beginning of nasal and the oral cavities. This is known to be pharyngeal cavity, and then following that we have a oral cavity, this is one, and here the above one is the nasal cavity. And the different parts of this will be as I mentioned here, the important parts, the area wise I have mentioned over here. Laryngeal cavity, that is around the vocal folds, and then this is known to be pharyngeal cavity, and then this is the oral cavity, and this is the nasal cavity. And so as we know that the speech is produced during the exhalation process, that means when you release the air, then only the speech is produced. But again, the smooth release or free release of air cannot give you the speech. So the release of air has to be constrained in the speech production system at different places. One of the places is known to be the vocal folds. So where the vocal folds restrict the airflow, the releasing of air, exhalation of air, and by vibrating, and with that the vocal folds closes and opens. So whenever vocal folds close and open and close frequently in the periodic intervals, then correspondingly narrow pulses of air will be released, and these narrow pulses of air will be propagated through either oral or nasal cavity, and some sound units will be produced. And another constriction will be along the vocal tract, where the vocal tract is completely closed, and with that the release of air will be blocked, and then the sudden release of air from the releasing the constriction, that acts as a excitation, and with that the some sounds are produced. So that way somehow the sound units are produced from the speech production system by constraining the exhalation of air at different places in the oral cavity, right? And the details we will discuss in the following slides. And more detailed view of the vocal tract. Here you can able to see the vocal tract or the speech production system is numbered with different numbers, and here accordingly as per the number the names have been given, the labels have been given. You can see here this is the one, the first is numbered as vocal folds, so this is the vocal folds, and then the 2 is the pharyngeal cavity, that is what I mentioned here, that is from the vocal folds to till the third one, that is velum, and till this point this is known to be the pharyngeal cavity, right, and the 3, 4, 5, 6, 7, 8. So these are the different places from the velum to the lips, like this is the velum, this is the soft palate, 4, the 5 is the hard palate, then the 6 is the alveolar ridge, then the 7th is the teeth, and 8th is the lips, right, and likewise this is your tongue, and at different places of your tongues have different names over here, right, and here the 14 is the nasal cavity, right, you can see that the nasal cavity 14, and 15 is the oral cavity, so this is the oral cavity, right, and then 17 is the trachea. This windpipe, this is known to be trachea, windpipe, this is connected to lungs chamber and all, and 18 is the epiglottis. So here this vocal folds area, this is also known to be glottis or the laryngeal cavity, and this is known to be glottis, and this is the epiglottis, that means above the glottis place, that is the epiglottis, right. So then coming to the various places of articulation, as I mentioned that the speech is produced due to release of air, right, due to exhalation of air, but this exhalation of air has to be constrained at some point, has to be restricted or constrained at different places along the our oral cavity and along the this system. So one of the places is 8, that is known to be the like a glottal or vocal folds. So here the release of air is constrained by vibration of vocal folds. It means that vocal folds will opens and closes. So because of that, the free flow of air is transformed into a sequence of narrow pulses and all, right. We will see that how they look like. Then there may be sometimes the pharyngeal cavity also might be closed for certain sounds, right, but some sounds they will be observed by closing the velum, by taking by constraining at the velum point where the entire air will be blocked here, and then after some time the velum will be released. So with that some sounds are produced, right. Likewise there is a blockade at point 5, at 5, that means nothing but at the velar point, then the soft palate or hard palate or alveolar ridge or the teeth or the lips. At different places the air will be blocked by placing the constraint at that place, and then releasing of the air from that constriction provides you or gives you a different sound units and all. So we will see that what are the various sounds that are produced by constraining the air at different places, and sudden release of that acts as excitation, and with that the different sounds are produced. So we will see that what are those sounds, where their place of articulation or where the excitation starts. All those things we will discuss in the later slides. And this slide is basically to know about the names or the labels of the different places of articulation or the different cavities that are in the oral cavity, that are in the speech production system and all. So the speech, the basic steps in speech production mechanism, as I already mentioned, these are some salient features, salient points from a speech production perspective. Speech is produced during the exhalation of air, as I mentioned, because we can't produce the speech during inhalation. Always the speech is produced during exhalation of air, because speech is nothing but some energy we are releasing in the form of acoustic pressure variations. So that energy has to be that will be released only during the exhalation of air and all. And the lungs and associated structure provides the required energy, as I already mentioned, and the vocal folds inside the larynx is the main excitation source, and the constriction, that is a total or partial along the vocal tract, is an additional source. As I mentioned, there are some sounds that are produced due to the constriction at the vocal folds, is nothing but due to the vibration of vocal folds, and there are other sounds which are produced by constraining the exhalation at different places in the vocal tract. We will see the details. And the supraglottal system, which includes pharynx, oral cavity, nasal cavity, behave like a time varying resonator. And here the speech production system will be viewed or will be like modeled as like we have a source and system, where here the system is nothing but the vocal tract system will offer as a system. And this vocal tract system sometimes actually here, because if the vibration takes place at a vocal folds, then the system that is above the vocal tract, above the vocal folds, it acts like a time varying resonator and all, right. So here if you can able to see, like suppose in your like 10th or +1 +2, where you come across the concept of the resonances, or like you have a tube where if you excite the tube with a tuning fork, so based on the shape of the tube or dimensions of the tube, we have a different sounds will be produced and all. It's nothing but here the vibrations that are generated from the tuning fork acts as excitation, and based on the tube structure, the different frequencies will be resonated and all. That means different frequencies will be more dominatingly resonated. So that way, in the same way here also the speech production mechanism also we can view it as an excitation source. From that the excitation will be released, and that excitation is propagated through a resonator, the time varying resonator, because it's a time varying resonator, because for different sounds the resonator shape will be different. For example, when I produce the resonator, or you can say that the vocal tract will be widely open. Like when you produce E, the vocal tract will be like like it is narrowly opened. Oo, there is some other shape. So likewise the vocal tract is dynamically changes according to various sounds. So that way we call it as a time varying resonator and all. That means with respect to time, based on the sound unit, the shape of the vocal tract will change, will vary and all. So that gives you the different sounds. Because in the case of our, as I mentioned example, when you excite the tube with a tuning fork, the output sound depends upon the tuning fork frequency, the characteristics of a tuning fork, as well as the structure of the tube or the shape of the tube and all, the diameter of the tube or the length of the tube and so on. The same way here also we can view the vocal tract system as a resonator, and the excitation that is obtained by either by the vocal folds or by the constriction at different places in the articulation is viewed as excitation, and this excitation excites the resonator or the vocal tract, and that gives you the different sound units and all. That was the basic idea about the speech production mechanism from a human perspective. So by knowing this, we will try to like perform the speech processing from a machine perspective and all. And here there are, as I mentioned, the speech production can be viewed as a combination of, as a joint effort of source and system. It means that the output speech, the characteristics of a speech, that depends upon the excitation characteristics as well as the system characteristics also, right. So from here we will try to see what are the different types of excitations in the speech production mechanism. So here we categorize the excitations into three types. One is a voiced excitation. Voiced excitation means here the release of air, or you can say the exhalation of air, is controlled or constricted by the vocal folds, by the vibration of vocal folds, because vocal folds will be there at the larynx, and the vocal folds will vibrate for providing the voiced excitation. Here vibration means they just open and closes and all in a periodically. So with that, the release of air, instead of free flow of release of air, it will be transformed into sequence of pulses, sequence of narrow pulses and all. And these narrow pulses acts as excitation, and that will be propagated through the oral cavity or a nasal cavity or supraglottal system. So with that, the different sounds will be produced and all. So that way the excitation that is due to the vocal folds vibration is known to be voiced excitation and all. And the speech that is really produced due to this vocal folds vibration is known to be the voiced speech, known to be voiced speech. And then similarly we have unvoiced excitation. Unvoiced excitation means other than the vocal folds, the excitation also takes place because of constriction at around the vocal tract, either partially or completely, right. So the total constriction along the vocal tract, as I mentioned here in the earlier figure, I have shown that at a vocal tract at different places the constriction can takes place, that is at a velum, then the soft palate, hard palate, then alveolar ridge, teeth, lips. So at different places the vocal tract can be constrained, can be completely closed, and then sudden release of that constriction acts as excitation and all. So that way either complete constriction or a partial constriction. For example, if you have a sound like sa, like sha, like sha. So all these sounds, for example, you can see that we will try to constrain the air, we will try to restrict the air, but there is a narrow opening will be there, with that the air will be rushed, that acts as a excitation and all. And whereas some other sounds like for example k, g, ch, ta, da. So for all of them, for these sounds for example, where the vocal tract at some point it is completely closed. So with that the release of air will be restricted by that constriction, and pressure will build up, and after reaching the pressure beyond a threshold, then this constriction no longer exists and it releases the constriction. With that the turbulence of air will be produced, or air will be generated, that acts like an excitation and all. So these excitations are known to be unvoiced excitation. Unvoiced excitation, and the speech that is produced due to this unvoiced excitation known to be unvoiced speech. Unvoiced speech. We will see the details, we will see the examples of sound units which produced in the as part of voiced excitation and as part of unvoiced excitation. And there are some sounds which are produced due to combination of both. It means that for example, if you take a sound unit like a g, like a j, so for those sound units both vocal folds will vibrate, and along with the vocal folds even there is a constriction also will take place. For example, g, where you can see a constriction at a velum, but during the constriction also the vocal folds will vibrate. So they are known to be mixed excitation and all. That means here for these sound units both vocal folds vibrate, and along with that the constriction and the release of constriction also acts as an excitation and all. So it's known to be like a mixed excitation, and the speech that is released due to the mixed excitation known to be mixed speech. So these are the three different types of excitations, and if you take any sound unit, so that sound unit will be resultant of one of these excitations, either voiced or unvoiced or combination of both. So here you can see the different sound units, and here the sound units are classified at a broader level based on the broader categories of like voiced and unvoiced excitation. Just now we have discussed. For example, if you see the vowels, so the vowels are produced due to the voiced excitation. That means all the vowels they produce due to vocal folds vibration. That means for the vowel sounds, the excitation is due to the vocal folds vibration. That means vocal folds will vibrate. So with that the release of air will be transformed into sequence of pulses, narrow pulses, and these pulses will propagate through the oral cavity. But the oral cavity will take different shapes, because of that different vowels will be produced. Otherwise across for all the vowels the excitation remains same. But the difference in the various vowels are due to the change in the vocal tract system, or change in the shape of the vocal tract system, or change in the shape of the resonator cavity, whatever we have mentioned. So that way the vowels are produced due to the oral cavity is widely open, and there is a tongue hump and a glottal vibration. Glottal vibration is nothing but vocal folds vibration, and the tongue hump, that means the position of the tongue hump, by varying the position of the tongue hump different sounds are produced. That means if you place the tongue hump at the front side of the oral cavity, that produces E. If you just try to visualize, experience, where you can see that the tongue will be hump, the tongue will be folded, and the tongue hump will be observed at the frontal side. And for example, U, where the tongue hump will be at the back end. Then A, somewhere the tongue hump is somewhere middle and all. Like similarly A, the tongue hump will be somewhere middle or slightly backward. So that way the position of the tongue hump will be responsible for a production of different vowels and all. But for all the vowels the excitation remains same, that is the vocal folds excitation or due to vocal folds vibration known to be glottal excitation or glottal vibration. Then coming to the unvoiced consonants, where the excitation is due to constriction of the release of air completely at different places in the oral cavity. For example, the unvoiced examples of unvoiced consonants are like, for example, ka, cha, ta, ta, pa. Ka, where the constriction is at the velum, ka. Cha, cha, where the constriction is at the palate, soft palate as close to that. Cha, ta, where the constriction is before the teeth, and ta, where the constriction is at the teeth, and pa, where the constriction is at the lips. So therefore, by restricting the air at different places, by providing a constriction, and the release of that constriction acts as excitation and all. A sudden release of constriction where the air will be blocked till that point, and the release of constriction, sudden release, that acts like an excitation, noisy excitation, and that is responsible for the sound units just now I have mentioned and all. Like those are the unvoiced consonants. It means that here for production of these unvoiced consonants, just an example I have mentioned, like k, ch, t, ta, pa. So these unvoiced consonants, so they are, for them the excitation is, the unvoiced excitation is nothing but the complete closure of the air at different places along the vocal tract, and release of that closure acts as excitation and all. But during this, for production of these sounds, vocal folds remains open. There is no vibration of vocal folds at all. And there is a voiced consonants. So the examples of voiced consonants are like g, g, j, da, da, ba, ba. So where you can able to feel that for the production of b, b, a g, where the vocal folds vibrate till the time of constriction, and the release of constriction, anyway the release of this sudden release of the turbulence of air, that acts as excitation. So that way for these sounds like g, j, da, da, ba, so where when I am uttering g, ja, da, da, ba, so there the vowel is also associated. The actual sound is what I mean to say, the voiced consonants means g, j, da, da, ba. So those are the voiced consonants where they are produced due to the combination of both the excitations, both the voiced excitation as well as the constriction, placing a constriction or providing a constriction, and release of constriction acts like excitation. Whereas the distinction between unvoiced and voiced is that, so both have the same type of constriction along the different places in the oral cavity, like ka, cha, ta, ta, pa, ka, cha, ta, ta, pa, and ga, ja, da, da, ba. For both of them the constrictions are at the same places, but the difference is that in case of ga, ja, da, da, ba, where you have a vocal excitation also there, you have a vocal folds also vibrate during the constriction time, during the constriction. Whereas in case of ka, cha, ta, ta, pa, where the vocal folds will not vibrate at all, vocal folds remains open. So that is the difference between the voiced consonants and the unvoiced consonants. Then coming to the nasal sounds, the nasal sounds are produced due to the vocal folds vibration. The nasal sounds are produced due to vocal folds vibration, but these are nasal sounds because, so the vocal folds will vibrate, but the pulses or the excitation signal, whatever is generated by vocal folds, so they are coupled to the nasal cavity. Right? How they are coupled? Here we have a velum. So this velum will be lowered, and the oral cavity will be somewhere it is closed. So because of that, the excitation is not released, or the excitation is not propagated through the oral cavity. So the only chance is that the excitation is propagated through nasal cavity and it is emitted through the nostrils. So that way the sounds like m, n, like where m, n, n. So these sounds are like nasalized sounds, where for that the vibration or the vocal excitation is the vocal folds excitation, right? But this excitation is coupled to nasal cavity. So it coupled to both oral and nasal cavity, but in the oral cavity it is somewhere blocked. So it means that the excitation is not released or not completely propagated to oral cavity. It is propagated to oral cavity, but it is somewhere blocked. So therefore there won't be any emission of speech from the oral cavity. So the emission of a speech is only through nasal cavity. So that way the nasal sounds are produced, right? So both the nasal sounds and the vowel sounds and all, so they are produced due to the voiced excitation, or nothing but they are produced due to the vocal folds vibration. And then there are other sounds known to be fricatives. It's a broader category, fricatives, and here the fricatives are produced by the excitation due to the narrow opening or a partial closure. So as I mentioned here, the unvoiced excitation is due to either complete closure, completely blocking the vocal tract at different places, and the sudden release of that acts as excitation. So that is unvoiced excitation, and in that unvoiced, some of them, for some production of some sound units, the vocal tract is not completely, we attempt to close that, but we don't close it completely. It's almost closed, but there is a slight narrow opening will be there. With that the air will be rushed, the turbulent air will be rushed through that acts like excitation and all. And those sounds, for example, the sounds like sa, sh, sh, ha. So these sounds where you have a vocal tract will be almost like about to close, but there is some narrow opening or partial closure will be there. With that the air will be rushed, and that acts like excitation and all. And that excitation, that is propagated through the rest of the oral cavity, and with that the different sounds are produced. Because for example, you have sa, sh, sa, sa, sha, ha. You see that those sounds like sa, 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 sha, ha. Those sounds you can able to see this partial closure is observed at different places in the vocal tract, like the way the ka, cha, ta, ta, pa. Similarly here the sa, sa, sha, ha in the reverse way, where the sa, sa is like where you have a narrow opening at the teeth, sa, 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 sa. Sha, where they have a narrow opening like the behind the teeth, somewhere in the retroflex or palate, like sha somewhere backside, ha somewhere back where the velum and all. So these are known to be fricatives, like a partial closure or a narrow opening of a oral cavity or a vocal tract at some place that acts like excitation and all. So here you can see these two figures, where here the figure that is in the left side, where you can see that the excitation is coupled to the nasal cavity. So with that the nasal sounds are produced. But here it is shown that it's a generic figure where the excitation signal from the vocal tract, from the vocal folds, it is coupled to either oral cavity or a nasal cavity. And whereas if you look at the second figure, it is clear that the excitation signal is coupled to only oral cavity. And here this controlling of coupling the excitation to a oral cavity or a nasal cavity, that is controlled by the velum. So this is known to be velum. Here you can see this part is known to be velum. So if the velum touches this here, then in that case the nasal cavity is isolated, right? So where whatever the excitation, the release of air is coupled to only the oral cavity, and with that the sounds are produced. All the non-nasal sounds, like except the ma, except ma, na, na, so except those sounds, remaining all sounds where the excitation is coupled to the oral cavity, or the speech is emitted through the oral cavity only. But those nasal sounds where, in that case, for production of nasal sounds where the velum is slightly lowered, so with that the excitation is coupled to nasal, and you have a nasal resonances will be produced, and that with that the sound appears like a nasalized sounds and all. So that is the reason for in our humans, For some of them, you can see that their speech appears to be mostly nasalized speech. The reason is that when they are producing the speech, the velum is not completely closing the nasal cavity. It's not completely, if it is completely closes, then you have a proper oral sounds or the vocal sounds used to be there. If it is not completely closed, then what happens is that, so maybe the majority of the excitation is coupled to oral cavity, but there is some excitations are coupled to the nasal cavity also. With that, their speech appears to be like, the entire speech appears to be like a nasalized one. Like for example, in India, like where if you observe the Kerala, the Malayali speech, where most of the Keralates, the speech appears to be a kind of a nasalized one, right? So maybe that in there mostly the velum is not completely isolating the nasal cavity. There will be slight opening or some opening will be there, slight opening. With that, a partial excitation or excitation is partially coupled to nasal. So therefore, their entire speech appears to be like a nasalized speech. Yeah. So this is a schematic block diagram. Just to visualize the speech production process. Whatever we discussed so far, you can see here, this is the lungs assembly. The muscles will enforce the lungs. So with that, the air will be released, or air will be during exhalation process. It's a kind of you can able to visualize the lung assembly like that. We have piston and this is forced towards this one. So the air will be released. Air will be released outside, released out of the lungs. So when the air is released out of the lungs, through trachea, here we have a laryngeal cavity where the vocal cords are known to be vocal folds will be there, and these vocal folds vibrates. These vocal folds will vibrate. So because of the vocal folds vibration, so here these vocal folds vibration is nothing but they open and close frequently or in the regular intervals and all. So when they close this, for example, and here when the release of air happening, when if we close it, then the pressure will build up, and once the pressure crosses certain threshold, then the vocal folds cannot hold that pressure and they try to open. So when the moment once it opens, then the air will be, suddenly the air will be released, and once the air is released, then the pressure below the vocal folds will be reduced, and again the vocal folds will be closed because they are the tight muscles, right? And when the pressure is more, then they slowly they release, and the moment once they release, here the pressure will go down and some narrow pulse of air will be released. So then again it closes, then again the pressure build up and again opens. So that way this vocal folds vibration acts like will transform this exhalation of air into a sequence of narrow pulses and all, and these narrow pulses will propagate through the pharyngeal cavity. It's nothing but from the vocal folds to till the oral cavity here, pharyngeal cavity, and then here we have a velum. This velum controls the coupling of the excitation to nasal cavity and the oral cavity and all. Here if the velum touches here, then the nasal cavity will be blocked, right? The entire excitation whatever is obtained, it is coupled to the oral cavity, so that way the oral sounds are produced due to mouth. And suppose if the for production of nasal sounds where the velum will be like slightly lowered, so with that the excitation coupled to nasal cavity, and somewhere here the vocal tract will be closed. Like for example in case of ma, where you can see that the vocal tract is closed at the lips. So therefore even though the excitation is coupled to oral cavity, but it's not released from the lips, right, because the lips are closed, and therefore the entire excitation, the entire speech, the sound is produced due to the nasal cavity, resonances of nasal cavity and all, right. Like for example na. So where the excitation coupled to both oral and nasal cavity, but the oral cavity is closed at the teeth, like na, where the oral cavity is closed at the palate, soft palate. So likewise we have a different nasal sounds where by blocking the oral cavity at different places and coupling the excitation to the nasal cavity, they are responsible for production of different nasal sounds. And yeah, Now, this is the diagram or a figure which shows the like as I mentioned that this vocal folds vibration transforms the release of air, the free release of air into a sequence of narrow pulses. So, here you can able to see that the glottal volume velocity, it is nothing but the release of air at a glottis because of the vocal folds vibration. The release of air, you can see that it appears like this. It is nothing but it is a glottal volume velocity. It is nothing but the velocity of air through the glottis. Because of the vocal folds vibration, you can see here, this is the portion where the vocal folds are opened. During opening phase of the vocal folds, you can see the velocity is very less, right. And then this is the phase where you can see that the closing is taking place. That means here till that the glottal folds are open, and here the closing starts. That means here this phase, transition phase, where the closing takes place, and here this is a complete closure. This is the place where almost like vocal folds are completely closed. And the moment vocal folds are completely closed, then the pressure beneath the vocal folds will go beyond the threshold, and again the vocal folds will suddenly release. The vocal folds, when they release a small gap, so with that the air will be rushed, and with that again the whatever the pressure that will build up, so that will be suddenly drops down, right. So, that way you can able to see this is the glottal volume velocity corresponds to vocal folds vibration and all. So, because of vocal folds vibration, the air that will be releasing, the release of air, the exhalation of air will be transformed into the sequence of pulses, right, narrow pulses. And these sequence of pulses, they propagate through the oral cavity, and then based on the shape of the oral cavity, right, the different resonances will be produced and all. Different resonances will be produced. Resonance means the energy will be concentrated in a particular range of frequencies or particular frequency, where, so because of that we can able to hear the different sounds and all. We can able to hear different sounds, right. If the cavity is very narrow and all, then the sounds that you can observe will be the high frequency sounds, and if the cavity is very wider, where we can able to observe the sounds corresponds to a lower sounds and all, lower frequency. That means the most of the energy will be focused at the lower frequencies if the structure or the oral cavity is widely opened and all. If the oral cavity is closed almost like very narrowly, so in that case you can able to see the sounds where the energy will be concentrated at the high frequency range and all. So, this is the glottal volume velocity, or you can view this as the excitation signal and all. And this excitation signal is propagated through the oral cavity, and the oral cavity will superimpose its response, its characteristics. So, that will be, so because of that the output speech looks like this. You can see the bottom figure, there are two figures. The figure that is in the top, it's excitation signal, or you can say that it's like you can say that it's you can view this as the excitation signal, and when you propagate this excitation signal through the oral cavity, and the resonance characteristics will be superimposed on that. So, with that the results speech, and now this is the speech signal corresponds to this excitation and all. You can see here, right, this is the speech signal, right. And here, because of this non-linearity and all these variations in the speech, this is because of the superimposed, the characteristics that are superimposed over these pulses and all, because this is the excitation, and this excitation will be modified by the oral cavity based on its shape and so on. So, this is the speech signal and all. This is the speech signal, right. And we can view the speech production system as a digital, from a machine perspective like this. This is your time varying digital filter, nothing but your vocal tract system, or you can say the supraglottal system. It means, suppose if the excitation is the vocal folds excitation, then the system, or you can say that the entire cavity above the vocal folds can be viewed as the resonator and all. Like, depending upon the place of excitation, the rest of the oral cavity or a vocal tract system can be acts like a resonator and all. For For example, in case of ka, where the excitation takes place at the velum. So therefore, whatever the vocal tract system beyond the velum is treated, will be viewed as a resonator and all. Like for example, ta. For example, ta. So where you can see that ta, where the excitation takes place with the teeth. So therefore, the narrow cavity between the teeth and the lips acts as the resonator and all. So that way you can see that in a digital context, where from electrical modeling, signal model, electrical system modeling perspective, we can say our time varying digital filter is nothing but your vocal tract system, and the excitation will be like a different, as we have already studied that we have different types of excitation. One is the voiced excitation, and the other one is the excitation due to the constriction, either partial constriction or complete constriction. So it is going to be unvoiced excitation. And in case of voiced excitation, we have seen that the release of the exhalation of air will be transformed into sequence of pulses. That is what we have seen in the previous slide, where you have a narrow sequence of narrow pulses, right. You can see here the narrow pulses here and all, right. So this is the excitation corresponds to the voiced speech. And whereas in case of the unvoiced speech or unvoiced excitation, where it is nothing but you have complete closure or a partial closure, with that the air will be released or turbulent, with the turbulence of air will be released, that acts as a excitation. So that is modeled as a white noise and all, that is modeled as a white noise. So therefore the excitations will be either a sequence of pulses, narrow pulses, or it is a white noise. A sequence of narrow pulses, these are modeled as impulses with the periodic intervals, and a white noise will be modeled as for unvoiced excitation and all. So that depending upon, you can see this is the overall speech production system. You have the excitation either from the voiced excitation or from the unvoiced excitation, or a combination of both, mixed excitation, right. So that way the excitation will be either voiced or unvoiced or a combination, and then the excitation will be have different based on the strength of the excitation, that is nothing but the gain represented by gain and all, and then this excitation will be given as input to the system, the vocal tract system, and based on the shape of the vocal tract system or the movement of various organs and all, the different frequencies will be resonated and all, or you can say that the energy will be distributed at different frequency ranges. Accordingly, we have a speech signal and all, we have a corresponding speech signal. And here you can say the excitation signal is represented by E of n digitally. It is a sequence, it is a discrete time signal E of n, and this E of n is either a voiced excitation or a noisy excitation, or you can say unvoiced excitation. And the characteristics of a vocal tract system is represented by H of n. Characteristics of vocal tract system is represented by H of n, and the output speech is nothing but exciting the time varying resonator, a time varying digital filter using this excitation. So outcome is S of n is nothing but the convolution of the excitation with the response of the vocal tract system and all, because by this convolution will holds good if we assume that the vocal tract system or the overall system is a linear time invariant system and all, linear time invariant system. But our speech production system, if you look at the vocal tract system, it is not a uniform tube. The structure is very complex and all, we have very complex structure used to be there, and but for the analysis purpose, analyzing a non-linear systems are very difficult. So therefore, even though the system is a non-linear system, we can view this non-linear system as a piecewise linear and all. That means suppose we have whatever the vocal tract shape, that vocal tract shape can be viewed as a combination of different tubes with different diameters or different radiuses and all. So that way any complex shape of a vocal tract system can be viewed as a combination of different linear tubes and all. So that way any complex shape can be realized using different tubes. So that way here we can view our speech production mechanism as a linear system it's not strictly linear, it's actually non-linear system, but this will be realized as a piecewise linear system and all, right. So therefore here if you look at this, E of n is nothing but excitation, H of n is nothing but the response of a vocal tract system, right, and S of n is nothing but the outcome of the vocal tract system, right. And here these are the discrete time representation or the signals in discrete time domain, and for their discrete time signals its corresponding frequency domain or the spectra will be represented by this way: E of omega, H of omega and S of omega. And we know that since if you formulate this system or vocal speech production system as a linear system, then you can able to write or you can able to visualize the speech as a convolution of the excitation signal with the response of a vocal tract system. So therefore you can write S of n as S of n equals to H of n convolution E of n, where H of n is nothing but the response of a vocal tract system and E of n is nothing but the input to the vocal tract system or nothing but the excitation signal and all. So S of n is nothing but the convolution of H of n with E of n. H of n with E of n, right. This is a time domain representation while modeling the speech production system as a linear time invariant system. In the time domain, the speech signal can be viewed as a convolution of the excitation with the response of a vocal tract system, or we can say that whatever the excitation is there, on that excitation the response of a vocal tract system will be superimposed on that, then the resultant will be your speech signal. So this is your in the discrete time domain, the S of n is nothing but H of n convolution with E of n, and in the frequency domain the equivalent one is nothing but that is nothing but the spectrum of a speech signal can be viewed as a product of the spectra of the time vocal tract system and the spectra of the excitation signal and all. So this we will derive this or we will discuss these things in the later part when you are discussing about the speech signal processing and speech signal analysis. So there we will discuss about slightly more about the characteristics of linear time invariant system, and in case of linear time invariant system, how the output depends on the input as well as the impulse response of a system. So all these things we will try to discuss more detail in that. Okay. So the next we move on to the speech perception system, and so here this is again a cross sectional view of our hearing mechanism, our ear and all, and here you can able to see that this is your outer ear, and this is the ear canal, and through ear canal this outer ear is coupled or connected to the middle ear. So this is the middle ear, and there are different parts in the middle ear, like at the beginning of a middle ear we have eardrum, and that is connected to, there are two other bones known to be like malleus and incus, and this is the inner ear, and then this inner ear, these bones are connected to the inner ear. This inner ear we have like a cochlea, where we have like organ that is like in a spiral fashion. In that the inner ear there will be liquid used to be there, and so this inner ear is connected to the hearing nerve, auditory, it is also known to be auditory nerve, and through auditory nerve whatever the resonances or whatever the the excitations that are produced here, so that will be coupled to audio nerve, and that will be reached to the higher centers of the brain where the message comprehension will take place. So we will see the details in a later slide more clear way. So this is the like a cross sectional view of hearing mechanism, and most of you are come across maybe in your like somewhere in the lower classes. So we can so the same thing whatever we have discussed here, the speech perception mechanism, where it basically consists of three regions like outer ear, middle ear and inner ear we have seen. So the outer ear directs the speech pressure variations towards middle ear, right. So because the when you produce the speech, so when you release from your lips, so it is in the form of acoustic vibrations or acoustic pressure variations, and because of this acoustic pressure variations, where this can be propagated through air through some distance, and there if the listener is present, then those acoustic pressure variations will be directed, will be captured by will be captured through this outer ear, and they will be propagated through the ear canal and reach to the middle ear and so on. And here the outer ear, if you see that, it has a very complex structure, right. So the shape and whatever the details of this outer ear, they are very important. It is one thing is that it directs the acoustic, captures the acoustic pressure variations and directs them towards the middle ear. And another very important thing is that the structure of this outer ear, whatever you can see, so this provides you that, this gives you that this can able to detect the directionality of the sounds. That means suppose the sound is arriving from a different direction, somebody is back, somebody is calling you from back, then immediately you will come to know that, yeah, somebody is calling from back. Suppose somebody is calling from somewhere in this corner and all, then immediately you can come to know that, yeah, there is a sound that is observed or that can be perceived from this particular direction and all. So that way the directional properties or the directionality or directional related, or you can say that the direction of the sound source is mainly like determined by the outer ear and all, because of this specific structure of the outer ear. So with that it can able to identify the from which direction the sound is, or from the speech is arriving, or the acoustic vibrations are arriving from which direction and all. So that will be clearly, you can able to characterize or clearly determine based on this outer ear and all. So that way the outer ear is very important to measure the directivity, or you can say that the directional characteristics of the source of the sound. Suppose for example, if you don't have outer ear, then you may hear, but you cannot make out from which direction the sound is arriving and all. So then the middle ear, the purpose of the middle ear will be like it transforms the pressure variations into mechanical motion, because as the acoustic vibrations are coupled to from outer ear to middle ear, so these acoustic pressure variations directly hit the middle ear, and the middle ear, we have the the eardrum will be there in the middle ear, the first bone, and the eardrum that vibrates as per according to this pressure variations, and with that it converts these acoustic variations into the mechanical motion and all. And then this mechanical motion is coupled to the inner ear. So where the inner ear converts these mechanical vibrations into electrical firings, and those electrical firings will be coupled to the auditory nerve and all. Auditory nerve, and this auditory nerve will carry these electrical firings, and they reach to the higher centers of a brain, where the language decoding and message comprehension, understanding will takes place at the higher centers of a brain. And here it's very difficult to visualize, or difficult to understand how exactly all these things are happening inside our the perception mechanism, perception system and all. It means to some extent you can see that we can able to analyze the characteristics of outer ear or middle ear and all, but the inner ear and all, it's very difficult to see that how the mechanical vibrations are converted to the neural firings and all, or right. So it's very difficult to see that. So very little understood from the perception mechanism, whereas compared to perception mechanism, we can observe that the production mechanism is, we have more clarity or more detailed observations or more detailed understanding is there with respect to the speech production mechanism. At least from the neural impulses, when they excite these, or when they try to vibrate these, try to move the various articulators as per different sounds with the different excitation sources, and by providing different shapes of the vocal tract, and different sounds are produced. So to some extent it is more clear compared to the speech perception mechanism and all. You can see here again the same thing. The acoustic pressure variations are funneled through middle ear by outer ear, and then the eardrum converts the acoustic pressure variations into the mechanical vibrations, and these mechanical vibrations are transferred to inner ear, from the middle ear, and here in the inner ear we have some liquid used to be there, and these mechanical vibrations, so they will create a standing wave patterns in the liquid, and those standing wave patterns are converted to the neural firings on the auditory nerve, and this auditory nerve carry those neural firings to the higher centers of brain where the message comprehension or understanding will takes place. And so from the mission perspective, we can view this speech perception mechanism as speech signal, and where like the way the spectrum analyzer will try to analyze that in the speech signal, so how the energy is distributed in different spectral, in different frequency ranges, right. Suppose for example, as we know that the speech signal, the range of frequencies will be like 0 to 20 kilohertz, for example, auditory range, and then the energy how it is distributed in this range 0 to 20 kilohertz. So that you can able to visualize in the spectrum analyzer. Similar to that, the perception mechanism also can be modeled or can be viewed like a spectrum analyzer, where given a speech signal, somehow you can able to see that how the energy is distributed in different frequency ranges, and accordingly with that the higher centers of a brain can able to interpret the different sound units and all. So with this we can conclude this lecture, and in next lecture we will discuss about acoustic phonetic representation of different sound units and all. So far we discussed about the production and perception mechanism from a human perception, and now we will see that how these sound units are manifested in the acoustic signal and how that can be visualized in the time domain and frequency domains. In view of speech production, so far we have discussed in the theory about how the various speech sounds are produced with the help of the excitation source and the vocal tract system, and here for better understanding of the speech production mechanism, so there are animations that are available at the YouTube created, they are available in the YouTube, and you can able to visit these following links, and where you can able to see the animations related to the production of different sound units. So here you can able to clearly visualize how the various speech sounds are produced, like the vowels, consonants, and again in the consonants there are different types of consonants like voiced stops, unvoiced stops, nasal stops, fricatives. Likewise each of the sound unit, how they are produced, like for the production of each sound unit, so what is the excitation source and how it is coupled to the either oral cavity or a nasal cavity, and what are the various articulators that are that can be that are part of the production of the particular sound unit. So all those things you can able to clearly visualized by in these animations and all. So in view of that, I recommend to follow these go through these links, and you can able to see the animation videos. So with that you can get a better picture of picture and understanding about the speech production, particularly to different categories of sound units. So that we will discuss in a next class. Thank you.